Alright, now we have just finished the amino acids and their structures. We'll be going through what I mentioned earlier, the positively charged and negatively charged amino acids matter and their groups. So, looking here, we have our topic, protonation and deprotonation. We have our pH scale, and as you know, from 0 to 14, the closest you are to 0, the more acidic it is due to the presence of the hydrogen protons, right? The more protons going that way. And as we can tell from our structure here earlier, we have our amino group side chain and our carboxyl group side chain. The carboxyl group has a pKa in which it protonates or deprotonates at 2 pH. So if it's less than 2 pH, the carboxyl group will become OH over here. But if it goes beyond 2 and turns to 3 or 4 or higher, the protons are lost. The proton is lost due to lack of proton in the solution, and it will deprotonate and turn into something like this, or here, right? The H gets lost and turns negative. It deprotonates. So in the native state, at physiological pH 7.4, you can imagine that the carboxyl group, the OH, is going to deprotonate, and similarly, or conversely, for the amino group, since their pKa, the pH at which their deprotonation or protonation happened is near 10 at physiological pH 7.4, that's going to protonate and turn NH2 into NH3+ due to the excess protons in the solution. So at 7.4, we have what's called a zwitterion. Zwitterion. Because it has both positive and negative happening on it at the same time. It has protonated state and deprotonated state on it. And you can see how I denote physiological pH should be 7.4, and this net charge of the amino acid is 0. I'm using glycine, for example, because it doesn't have R group charge on it right now. It's just H. So you can see that when it's around pH 1, both the carboxyl group will be protonated, so it retains its H on it, so now it's 0, like neutral on this side, but the amino group is still protonated because it's obviously more acidic than its native pKa, so it has a positive charge, so the overall charge is +1, right? +1 plus 0, that's 0, whereas this is +1 plus -1, so that's 0 net. And you have your when it gets really basic and turns to 12 pH, the environment doesn't have enough hydrogen atoms, so the carboxyl group gets deprotonated and the amino group turns to native state, so neutral. So overall is -1 plus 0, so you get -1 for the overall charge of the amino acid. I have done the positively charged group, as we saw earlier. This is lysine. Lysine over here has additional R group that has a physiological pKa, at a pKa of about 9.5. So that means at around 8.9, around 9 pH, it can turn from protonation or deprotonation for the R group specifically. So the NH2 group gains gains a charge, a positive charge, when it's less. The pH is less than that. But when it's more than that, if it's like 9.5, more than 9, the proton will get lost here and it will turn back to its native state. So you have your all the way to the end where both the carboxyl group is fully protonated, as well as your amino group and your R group. So you get 2 positive charge in total, so you have +2 at this pH of 1. At physiological pH of 7.4, you have both of them still protonated, but since 7.4 is more than 1, the carboxylic acid is deprotonated, so it's negative. So +1 + 1 -1, you get +1 in net. And as I showed earlier, 9.5, since it's more than the pKa of the R group, and the R group pKa can be determined from a table, so you don't actually need to memorize all of that, except for you can kind of think about it. Positively charged means that physiological pH 7.4, it's +1, as opposed to like a net neutral for our nonpolar group. So here we have 0, +1, -1, so net will be 0 charge at 9.5 for lysine. And you have all the way to 12, right? 12 is bigger than 10 for the amino group pKa, so you have a -1. So it's 0, 0, and then the carboxylic acid is still deprotonated, so -1. And so conversely, for your negatively charged, you can see that here we have aspartic acid, and that physiological pH is negative at 7.4. 7.4 pH, it's negative because this group has a pKa of around 3, a bit more than carboxylic acid, so at pH greater than 3, it's going to deprotonate. I think it's more than 3, like 3.5, 3.6, but it's going to deprotonate, just like how carboxylic acid deprotonates above 2 point something. So this deprotonates, so negative, negative, and plus the amino acid, which is positive at this pH, you get -1. And you can see for all other examples, at 3, since only the carboxylic acid is deprotonated, you have -1 here. This gets protonated because the pKa is 3.6 and here's 3, so there's enough protons in a solution to give it the proton. So neutral, and amino acid, of course, amino group gets protonated because it's way too acidic for its pKa of 10. So neutral, positive, negative, so you get net neutral of 0 charge. And here all of them are protonated, so +1 general, and to the other end of the spectrum all of them are deprotonated, so minus, minus, and then amino group is at its neutral state, so -2. Great. So now we have our bonding. For bonding, it's very simple. We have the nucleophilic amino group go ahead and attach the carboxyl group. So N attacks C. Boom. And this OH gets yoinked down and pushed out of the solution. So the water molecule gets taken away. So you can call this a hydrolysis. Is it hydrolysis? No, it's a condensation reaction. Sorry. It's a condensation reaction because water gets taken away, and it can also be called a dehydration reaction. So making proteins and amino acids bind together, forming a chain, makes them more dehydrated. You can think of it that way. And we have your N terminus starting from the amino side to the C terminus to the other side. When you have 2 amino acids together, you have your dipeptide. When it's 3, it's tri. Oligo is when there's multiple together, up to 20, and poly when it's more than 20. Yeah, tripeptide, oligopeptide, polypeptide, so forth. Alright, let's quickly go through the structures of the potential peptide chains. So for a primary chain, you just have your amino acids linked together, and for a secondary, you can either have alpha helix, which it turns and spins, or beta pleated sheet. So you have your normal group together, right? That's your polypeptide chain. And the secondary structure happens when the hydrogen bonds happen between the groups, and you get either kinks like this and twist together like helix, or you can get pleated sheets that go like boop, boop, right? Boop, 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 and form a stabler structure due to the hydrogen bonds. Your tertiary happens due to the extra bonds from the R group to each other, such as your hydrophilic interaction between the positive and the negative charged groups, or maybe due to your cysteine bridges. As we saw, the S was prone to oxidation, so many interactions could happen between the R groups, and quaternary is just the same thing as the tertiary, but you could also have multiple chains coming together and get clumped together into your globulins. Alright, that's basically a crash course on the pronation depronation parts of the amino acids and getting into the polypeptides. Alright, we'll see you in the next chapter. This is Alan. Bye-bye.